it. So the embarrassing bits are gone.
Yep. So this is Careers in Tech Summer Series event. Our speaker for tonight is David Alan Grier. Primary hosts for tonight are the Computer Society and Communication Society, as well as the IEEE section in Northwest Florida, as well as about 20 or so other chapters and entities scattered across regions 1 through 7. And without further ado, I'm going to pass this back over to David Grier, our speaker for tonight.
And thank you. It's just very nice to be here. I'm always pleased to be involved in chapter and section activities because I learned so much in the process. I'm talking about what I'm calling the generations of computer science. It's a subject that's quite dear to my heart. I think many of you may know enough of my resume to know that I have been president of the Computer Society. I was editor of Computer, been very active in the publications realm for much of my career. But what's not often seen is that my father was a computer scientist. He got a very early start in the computer industry in '52, which is about as early as you could get started. And then beyond that, my grandmother, which is sadly not the direct lineage grandmother, it's my mother's mother, was trained to be a human computer at the University of Michigan. She has a degree in mathematical computation in 1921. So because of that history, I've just gotten very interested in who the leaders are, what skills they have, how those skills evolve, what you need to do to think about your career for the future, what signs you need to follow. I will have some predictions here. I have great confidence that many of them are wrong, but I think I show a process that is useful to understand as we look at the changing field of computer science. So I'm looking at what are the skills needed to be a computer scientist, and I'm really looking at a leadership class here. I'm looking at a concept of decisive skills and roles, the things that we feel have to be part of a computer scientist to be a leader. And then once you do that, I'm taking you through an admittedly biased, but I think arguably interesting tour of different generational leaderships, how things have changed since '52 to the current day. What have been the dominant technologies? How have those been evolved, brought into the leadership skills? And what are the alternative technologies that we're facing now? And I've got a couple that I have thrown out, and I suspect I will finish the talk and someone will say, but what about? And then I'm going to give you a bit of a view of the future. And the interesting question that this sort of hangs on is, are computer scientists losing control of computer science, or in particular, what it is? So that is my outline, and that's the tour you're going to get from me tonight. And we're going to start with this picture. This picture is a picture of Lois Lurgans, who was an operator slash programmer slash mathematician at Los Alamos in the late '40s and early '50s. I love this for several reasons. First, it's just a lovely shot of her. And it's also a shot, like so many big iron pictures, of a woman gazing fondly into the eyes of a piece of hardware. But also Lois's daughter, Sue, was on my PhD committee in the '80s. So again, this is a bit of a family picture. And if you look at the background she had, she was basically solving numerical problems for physics, did a lot of partial differential equation systems, and did machine language coding in a way that I don't think anyone here can imagine. I barely can. Subroutine protocols, in that she did her own subroutine calls. She made up the protocol for how subroutines worked for her programs. And memory management when there weren't disks, when you were doing it by hand and when you were swapping things in and out to tape. That was the skills you needed in that era to be a computer scientist. If you look at the journals, if you look at the conferences at the time, those were what the papers were about. The people who were leaders of the societies, the leaders of the field, had skills that dealt with those sorts of things. Now, they're still part of the field. They have not gone away. We still have experts in machine language coding and in subroutine calls and all of that. But it's a teeny part of the field. Numerical analysis is still thriving. It's done a lot of interesting work since then, but it's also a small part of the community. I gave a version of this talk in Stuttgart several years ago, and this is the staff there. And there's a group that I could help them see their connection to the history of computing, and also point out that their role was now very specific, and it no longer shaped the field the way it once did. Something that both worried them a bit, but also gave them freedom to explore new ideas. And so when we're talking about what is a computer scientist, we're talking about decisive skills, skills that we need to have to be leaders, to be part of the field. There's also a bunch of skills that are kind of apparently decisive. And I have this lovely photo of the radio flyer wagon. Some of you may remember that from your childhood. As a child, you probably never thought about the two fundamental aspects of this toy. It had no radio, and it doesn't fly. Some of you may have tried to make it fly. I certainly did not end well. The name, it's a 1930s toy, and the name stole from the two most popular technologies of the age that were exciting young people to follow their career. But the name hided some very decisive ideas. It was a mass-produced stamped steel toy. And the company that made it did a lot of very creative work to make that happen, to make it the dominant toy that it was. But those skills were largely hidden by marketing, by public assessment, by how the toy company wanted to perceive what it was doing. And so that's what we kind of have to guard ourselves against, because we have a lot of skills that really aren't important to what we do, that we love. And so we have to ask, what's the nature of the field? Who's a leader? What is the intellectual foundation we've built upon? All of these, and I can attest from having been Computer Society president, will get a good fight at almost any conference. Raise any of them and bang, you're in it. One of the reasons for that is that computing is an avaricious field. It has taken ideas from basically every element of human endeavor. The foundation of it in the 50s, and we have to be careful here, were mathematics and electrical engineering. And those two members of those two fields kind of jostled back and forth about who would be in charge. In saying that those are the foundations, we forget that Babbage did an awful lot of foundational computer science in mechanical engineering. So did Konrad Zuse in the 1940s. So to bring in electrical engineering as a foundational tool misses some of the way things change. Some of the other things we have borrowed heavily, we don't admit this one bit, from factory and system engineering. The most obvious place is our definitions of software quality. Those come quite directly from Walter Schuhart, from W. Edwards Deming, and they've become part of our language as if we invented them. We've taken a lot from management, scientific management of the 20s and 30s, but military management has evolved in the 70s. Economics is a part of it, and so is psychology. All of these things have provided material for our field. Now, getting in there, I have to kind of help define what I'm talking about. And this greenish blob explains everything. You look at it and you say, ah, yes, a greenish blob. I understand it. You can go on. The area that I'm talking about is in many ways the yellow band. And it's all very fuzzy because the boundaries of our field are fuzzy, something that has been true of it since day zero. That shell of yellow is what surrounds a basic set of technologies that we work with and interacts with a green ecosystem, hence the green. I was playing off that. And that set of skills depends both on the technologies that we have and are working with, and also what the ecosystem needs. I've always liked Herb Simon's definition of the artificial, the science of the artificial, as applying to computer science. He argued that it was essentially what can be mechanized. And that question has both a technological component, what do we have that we can use, and an ecological component, what needs to be done. And so we're working in that area, and you can start listing off qualities. And this is a basic set that is really from kind of late 20th century, but most of them are still there. And you can see qualities, things such as the first four: mathematics, logic, switching circuits, machine architecture. Certainly when I was gaining my skills, these were central to computer science. And to be a prospective leader, which my father wanted me to be, he taught me all of these things. Some of my best memories were as a seventh and eighth and ninth grader, working with Dad, having him teach me logic, going through the books of Knuth to help me understand machine architecture and how machines worked. Those remain in place, but their role has shifted over the years. We then have a set of core skills: programming, system integration, system security, system design. Some are newer than others. Some, like system security, are surprisingly old. We have papers on system security from the 50s. And this is one of the key bits that I have to warn you about. The IEEE has a lovely electronic library. ACM has one too, but we're an IEEE group. I love that. And I go back and I read old papers. My goal is to understand how this field has evolved, where it's been, and where we're going. And to discover that system security has fairly old roots is one measure of its importance in our field. The last four, of course, are skills that some people have, some don't. Quality assurance is big for software engineers. Data architecture is not always. Statistics is an increasingly big part of the field, as is game theory, but not everyone uses them. So how do you put these together to make a leader? And I'd like to take you on this generational story. It is highly subjective, but I can make an argument about why it's interesting. We can divide our technological age into 6 or 7 or maybe 8 generations. If you start in the 50s with John von Neumann, you have bespoke computers made by hand with soldering irons, no two of them exactly alike. We get a second generation not that long after that's product. Certainly by the end of the 50s, we have standardized products, and early 60s, we start getting families of products. But I think there's a shift in there. And the next group that becomes interesting is operating systems, when that becomes part of our computer environment. And just in case there's a question about family pictures, that's my dad. He worked for Burroughs. One of the interesting bits of that picture is that he and I cross our arms in opposite ways. Don't know why that's a thing, but there we are. Fourth, we move into small computers, which in some level is just size, which I'm always cautious about when someone says there's a major transformation because computers are smaller or faster. But what happened was the ecosystem changed, and different people became involved in saying what they needed from computers and how they needed to operate. The fifth, which overlaps it, and I put it this here for a purpose because of the 5th generation project in Japan. High performance computing really starts going in a different spin in the 70s. And with it, takes many of the classic structures, but also acquires new kinds of programming skills that largely don't evolve beyond it. The skills of parallelism and how to deal with that is something that is, while not unique to high performance computing, dominates it in the way it doesn't dominate the rest of our field. Networking. That, of course, starts in '68. This picture is one taken for the 20th anniversary of ARPANET, which I believe it was taken in 1986 or 87. But that changed something. It ties very neatly into the operating system world. And it changes or reemphasizes different ways of communicating and sharing and working together. New skills become important as the network era grows. And finally, we have the one from the most recent change, early aughts, the cloud mobile model, in which computing becomes a commodity, in which small devices like phones become a major input-output device, and we start distributing things to the edge, with edge computing, and fog computing, and cloud computing, and all the rest. And there's a shift of what skills you need to be a leadership of that. So that's highly arbitrary, except it starts showing some interesting patterns. If you go through the years, von Neumann's computers operational in 52. We get products by 58. 68 operating systems are common. 78, we have micros. 84 is the highlight of the fifth generation project. Networking, 95 is the start of the internet. And 2006, 7, and 8 is mobile cloud. And you see a decade and some period similar to that between these dates. And then we start pondering. Okay, a human career is 30 years. Peak contributions probably about 15. It takes you a couple of years to figure out what you're doing. You develop your basic ideas early. You have a nice run of them for a period, and then there's a mop up at the end. And between these sort of periods, there are inflection points, intergenerational transfer of skills. Old people telling young people what they ought to know and often being wrong. A friend of my dad's spent a better part of an afternoon explaining to me why I really needed to know not assembly programming, machine programming, and in particular, why I needed to know memory management by hand. Never used it. And he's a lovely guy, but that was a generational skill that didn't come across. But there are a couple of things that are also important here. Our field, not quite uniquely, but close to it, has been tremendously effective in commoditizing knowledge, putting it in a black box and saying, here, you can use this. You really don't need to know what's going on in the box. You need to have a model, though, of what's being done. In my life, for example, for the IEEE, I was one of the leaders in what was once called multimedia and then became known as podcasts. And I became an expert at producing them without knowing a whole heck of a lot of what the algorithms were doing in the software I had, but in knowing something about signals and sound and microphones and how to put them all together. The software was a black box to me, and I never learned it, but I was able to make it into an efficient product for the IEEE. And with these come changing questions, different problems that we want to solve. So in terms of commoditization, a key inflection point we discover is software engineering in 68. So much happens between 68 and 70. It's hard to avoid that as a key inflection point. Software engineering, the key event in 68 for that is the Garmisch conference, sponsored by NATO, with a goal of producing better software, error-free software. The conference, the proceedings are online. They are fascinating. They argued for three different ways of engineering software. One, McElroy of Bell Labs argued for standardized parts, which became libraries. He could not articulate what that was and what he was trying to do, but he said if we make software like gears, we can then assemble good systems. Second group was Dijkstra's group from the Netherlands. He argued that we had to put software in a common disciplined form. What happened, his ideas eventually got incorporated in the editors and tools we use. No one thinks about it anymore. But it was important, but it wasn't enough. A third group argued for common languages. Well, that was already starting to build with a variety of groups of people supporting it. Because we had already had Fortran, we had stumbled a bit with certain languages like PL1. C is just around the corner. Pascal is in play. These were good, but they weren't enough. This is part of the discussion that goes into determining what's a decisive control. One of the dominant solutions that come out of it, one that everyone in fact has to learn and then largely argues against, was the software lifecycle, which is cemented in place by about 85. The paper here, this is from a paper by Barry Bone in Computer. Again, I recommend reading old issues of Computer because I think they're great. This is the software lifecycle. You can see it spinning out from a center, going through a design, build, test, evaluate phase, and going out from the center is an indication of how far the software system is to being done and also how much money you've invested. It was an idea that became central and dominated software engineering for a period. And then the Agile people came about 15 years later, and that 15 should be a thing you remember. And all of a sudden we're fighting against it and yet using it at the same business. So as we look and think about these cycles, we need to start thinking about what's going on. In software engineering, the commoditization occurs in the 90s. IEEE SWIBOC, software engineering body of knowledge. That commoditized an awful lot of software engineering. You cannot underestimate what Java did for the field. We had common languages before. That produced a body of software that remains in place to this day and a body of workers that remain in place. But what happened also is a larger cohort of workers with broader experience, with broader needs, and with new questions. In particular, the customer-centric idea started bubbling to the surface. And that, as much as anything, caused the break that moved us into Agile. So let's go back to this 30 years for a human career, 15 years for peak contribution. Can we identify, or at least get estimates, of intergenerational transfer of skills, and ask in particular, where are we now? We're going to have a timeline, starts at then, ends up at now. 15-year intervals, 52, 67, 82, 97, 2012, 2027. They don't quite line up with some of the key changes in the industry. I have a paper somewhere that I did on the role of recessions in shaping the computer industry. And it turns out the 4 major post-war recessions line up nicely with major transfers in technology and leadership. But this gives us a rough idea. The first period is the growth of high-level languages. Admiral Hopper was a dominant leader in that. There's a big fight over what she did, and it doesn't really matter what she did, but she was the lead advocate, and the skills she was advocating for were the skills the field had. Time sharing starts creeping in just before it. Relational databases are about 5 years after 67. We have object-oriented code in the 90s, in the early 80s, networking in the late 80s or that's pinned off of 95. Cloud mobile slips in there in the early 2000s. Okay, what does this tell us? Over this period, we start seeing changing skill sets. In 52, when we start, we're wiring computers out of discrete components with a soldering iron. Integrated circuits come in there in 1957. That's a major shift, and all of a sudden that changes the way people start thinking about computer engineering. You can now have things with a gate on it rather than just a transistor, just a single unit. Processor chips come out in the early 70s. And if you look at all of the computer journals, but computer is fascinating. I had initially speculated that we would resist, that there'd be a group of people arguing for keeping the older school of design. It's gone. People were willing to accept someone else's design of an architecture and build systems upon them. The floating point standard, that in many ways puts a major nail in the coffin of numerical analysis being decisive, because now all computers are running the same kind of floating point, and you don't have to do the kind of analysis that people had to do in the 50s and 60s to ensure that your answers were accurate. These are the kind of skills that are changing over this period. If I were to do a further divide, and I'm having to shuffle on my screen my little bar around so I can see my slides. Sometime around 1980, the decisive skill set shifted from hardware to software. If you look at the membership of the Computer Society in the 70s, it's still largely electrical engineers and people with that kind of background. But the Computer Society was formed in '67 with the direct intent of allowing people to join the IEEE who did not have a BS in electrical engineering. It's a long, hard fight. But when the final description of how the organization was going to come out, it said that you could have a degree in some other professional field. And it listed engineering fields, it listed mathematics, but it also ended with "and other fields." So at that point, we see a sudden shift. And that shift is to software being the decisive point, which is still largely where it is, although we'll talk about that in just a moment. And sometime in the late 80s and early 90s, we see a number of things that are starting to encourage the black boxing of software. SWBOC being one of them, that's coming out in about 94, 95. But other aspects of taking that idea and putting it in a box and giving that to people without the skill, without the knowledge of what goes on inside. All of that is changing what does it mean to be a leader. And that, mark roughly, is the difference between programs and systems. We now don't teach a programming language when we bring kids in to teach basic things. We give them a full development stack, which includes databases from day zero. We start thinking about how you develop a program that runs on a phone or runs on something connected to the internet with appies. So very early on, we're teaching kids, we're connecting you into systems. You're not running alone. And that's another key decisive point. There's one other, because I always do this. In around 2009, I discovered that I was the world's greatest rating expert on crowdsourcing, and I was that rating expert for about 15 minutes, or probably the better part of a year before that went. I'm fascinated with the connection between computing and labor, and that gave me the skills to work with the group that was developing it. Some of you may remember the Red Balloon Challenge, where ARPA parked 10 weather balloons in public places in the US, didn't tell anyone where they were, and said, go find them. And a team from MIT put together a game theoretic model that found them in 8 hours or something like that. And that was the mark of incorporating people as part of the systems. We are now doing systems that have computers, that have data, that have communications, that have sensors, and have people as part of them. And to be a leader as a computer scientist, all of those need to be part of your thinking. So, where are we now? I see us at a point of looking at a convergence of about 5 technologies. Cloud computing is probably the biggest and the most important for us to consider. It's the ubiquity, and by cloud, I'm incorporating a huge amount of distributed computation in one term. Computing as a commodity, computing that can be put at the right part of your system at the right time. So fog and edge gets thrown in there as well. The idea of being able to, move and incorporate data from all sorts of sources, of being able to move processes, because processes are often easier to move than data, or cheaper to move. That's been a key change in how we think about the traditional algorithms of computing and many of the traditional skills. So that's our first technology. The second one is Internet of Things, and you'll see this is leaning towards a data-centric world. But the amount of data that we're able to collect and the amount that we're able to get mechanically, it expands hourly. It incorporates so much of human endeavors that nothing we do is not recorded anymore, it seems. But it also gives us a new way of thinking about things. And in particular, we have learned over the last years that data, as I said, expensive to move. It often needs to be kept in separate places in ways that make it tricky to combine it. And how do we work with it? And how do we get answers that are good and useful out of it? That leads us to the third thing, big data, which is the mechanisms of handling all of these things. Um, it's a set of skills that, while they existed in the 80s and in the 90s, have taken on new life in the last decade. And it's difficult to go out and be a leader in the field without understanding what's there and how it's used. My favorite bit gets thrown in because, as I said, we're not building simply physical data computational systems. Human gets put in there too. The picture here is Samasource in Kenya. Samasource is one of the major cleaners of data that's used for AI training. And they do it as a crowdsourcing model. Because of where they operate, that their founder was very keen on utilizing labor in parts of the world that did not have access to industrial jobs. She put things in Kenya and certain parts of India and other places in the world that simply did not have industrial jobs. But how do these people react? How do they think? They not only clean data for AI, they review basically everything on social media. It's a tough job. It's a hard job. It's work that we need to do better jobs about protecting the worker, helping them do their tasks, getting their judgments right. And at the same time, we need to find new ways of engaging human judgment, in particular with things of game theory, mass market psychology, that help us understand what the world is doing and how we can respond to it as leaders. And finally, and all of these things point to what we've been dealing with for the last 5 years, machine learning. The algorithms of machine learning, date to the 70s. The kind of processors that we have that make them practicable are from the 90s. Big data and Internet of Things are slightly newer, but that process has been in play. And there's a huge public debate over what artificial intelligence is at the moment and how it's going to destroy the human being, and that may be true. But the thing we need to also remember is that it's becoming the default way of understanding the world. It is, in many ways, like statistical models, but statistical models with 9 million parameters, or even more. And that because of that, that's increasingly the way we understand complex phenomena. And to make design changes and manage complex phenomena, we need to understand machine learning. So all of these are the confluence that we're facing right now. There are a couple others that I will mention later. But it's to do this is what we need to do: innovation at scale. Computer science has always argued that it's there to help the world at large and help people live better, richer lives. That's been true of the literature since day zero. How do we capture human experience? How do we eliminate and reduce the programming time, the time to create systems to help people understand human experience, and we hope make it better? So we need to go back and start looking at the ecosystem, because that turns to shape what we do a great deal. The people who are asking the key questions about what computing is in the world, what it should be doing, and what needs to be done to make it effective in helping people. These leaders tend to be coming from business. And again, this is part of my argument that the connection between computing and labor, computing and production is huge. Chester Bernard from the 30s was important in defining what computing was. He was the president of AT&T. He wrote several key books on management and on managing large organizations, and talked about the need for having data for what was going on, processing and understanding it. And while you're doing that, using that technology to do some of the work, because the human level systems at the time simply could not provide the necessary services for everybody. The next time we get someone is the 50s, and this is Peter Drucker. Many of you know who he is. Drucker trained the managerial leaders of the late 20th century. Anyone who was a senior manager between roughly 1955 and 1995 had Peter Drucker in it. Drucker was a strong advocate of markets and of making sure that managerial decisions were based on market decisions. And because of that, he was very interested in what he called the knowledge worker, who processed information from markets, and leadership that made use of it. He never quite grasped how computers worked. He's just a little before the time. But he was asking the questions that you see being answered in the literature of the 60s and 70s in our field. Certainly, the relational databases come directly out of the kind of questions that he was asking. Tom Peters is his successor. Peters wrote a book called Excellence that stands unique in the computing field in that it highlighted 9 companies that were making good use of data and database management techniques. All of them have since gone bankrupt. That criticism often misses a key point. Peters grasped that the business world and the world in which computers operated was dynamic, that it was moving fast, and that people couldn't stop and rest on their laurels and say, this model is going to be with us forever. It's going to change. He grasped, before it really had a permanent name, things like Moore's Law, that the industry itself would be having a rapid turnover. And the questions he asked became the questions of how do you provide stability in that changing world that dominated computing probably until 2001. The one who brings it home is Clay Christensen. Clay Christensen is solely responsible for the use of the word innovation in its current definition in public discourse. Go to the New York Times, look up the word innovation, and see what articles have it in its title from then to now, and then start doing a histogram by decades. It's rarely mentioned prior to 1980. Christensen grasped ideas which others had articulated, but that crises moments in technology and crises in business would shift resources from old technologies to new, to technologies that had reached their limit or were perceived to be reaching their limits, to technologies that promised more opportunity. And with that, we have the whole innovation culture that we currently have. And my judgment of it is that that still has a couple more years to run. But that idea shapes where we are. So the question now is, what's the direction for the next stage? We're seeing it fought out in public. We have a couple business leaders who might want to claim that they're asking the questions, Mr. Zuckerberg and Mr. Musk being 2. Don't think it's them. But there is something about how we deal with the world at large, how we deal with human activity at large, how we provide the technologies that help us understand it and guide it and manage it for the good of all, that we're looking to sort through. So my feeling for the skills for the future really look at those 5 technologies and say, what is it in data, in the processing of data, in modeling data, in projecting from data, in all of those things, in building systems that make judgments from data. I've given this talk enough times that someone sticks up something that quests in the chat and says, but what about quantum? And it's a good question, and it's a question that I should have been more on top of, because when I was editing Computer, we spent a year arguing about where quantum was, what role it was going to have in the magazine, how much were we promoting something that wasn't there and may not be ever have a future, to something that we really needed to promote and get ahead of. It kind of came to a head. We got a special a proposal for a special issue that was quantum computing, blockchain, Internet of Things, and climate models all in one. And the editorial board just kind of put its head in its hands, going, all are good things. We don't know how they all relate. The proposed editors need to come up with a better argument. But behind it, there still is a good question. This is a new form of computation. There are new concepts. Using Boolean logic isn't enough to understand how quantum works. There's new engineering involved, that even though transistors required an understanding of quantum effects, this is a whole different level. And the programming is now quite different. The question is this going to be a decisive technology? I don't know. I need to be clear about that. Certainly from what I saw from the role of computer, my role there, I've got some questions about it. It's not, I'm not saying that it isn't going to come out with useful products, that it won't be out there and doing good work. The question is, what's the role it's going to have in our field? And one of the things that sort of caught my eye when we were doing it is this picture, because this picture is of a quantum computer as it would never be displayed. Quantum computers at the moment have to be chilled. It doesn't have bright colors and bright lights on it. This is an old 1950s, let's show off our hardware to show that we're smart picture. So that's not what we're going to get. It is likely, I think, that it'll be a specialist form of computing, a back end, if you will. That certainly is doable, and there is evidence that we're getting close to seeing something that might do it. Still a ways from a product, but it could easily come. A general purpose machine is not in sight right now. The stuff that we were seeing at computers was saying a decade at least, probably more. And the question is, there may be no reason to do a general machine. We have so much invested in what we've got that may require more re-engineering than we want. It could be decisive within the high-performance computing field. This could become the dominant skills for that field. Certainly, high-performance computing has seen a couple shifts. In the late 80s, before the late 80s, it was dominated by expertise in certain rarefied architectures and in a certain form of parallelism. After the 90s, it very much shifted into multiprocessors. Initially, the shift was in very conventional architectures. They now have a variety in them. But it's also become that high-performance computing is not that different from data centers at times. In fact, if you look at the list of the top 500 computers, several of them are data centers. So this could pull high-performance computing in a new direction, split off those that are really interested in primarily scientific but other complex pattern recognition problems. It'll be interesting to see. So quantum may have a chance to do it. The current fascination with AI, that's particularly the generative AI. Part about it is, I think, this is a little closer to our skill set. It's going to pull us a little less. It's easier to place in our field, and many of the skills that has are obviously part of our field already. But it's black boxing. It's pulling things in to boxes that others will use who don't understand much about how machine learning works, or how you have to deal with the expansion of parameters, or the difference between the various forms of neural nets that are at the base of these. That will more likely shift the outer ecosystem than it will shift us. In fact, I pulled these things out of the Washington Post. One is from today, the other one's from a little earlier. Two headlines. The Washington Post tends to write headlines that are politically provocative. Federal regulators call AI discrimination a new civil rights frontier. ChatGPT leans liberal, research shows. These are systems that, in both the articles, that people have used, that have been put together by people using AI as a black box. They don't know what's in there, what changes them, what makes it. And in particular, it's not clear to them about how you manage AI and how you manage the inputs to it to get the results you want. We have a lot of history about how to manage modeling programs. I did a term for a long time in the simulation world. And that's a field that says, this is the phenomena we're trying to model. This is what we've got as inputs. This is the system we make. We know how to check the two. We've got ways of doing that in AI. We have not gotten that out to the full field. But again, I think there are issues that will be part of our field and fairly obvious, but it's not going to pull it anyway. Much of the debate I liken to the radio flyer debate. It's a familiar reaction. We're taking a high level novel technology and novel words and applying it to stuff that we have used and we have been developing for a long time. And may or may not ultimately change the direction of the field, but it's certainly going to be part of it for a while. So we're at the end game. You're looking at your career, and I'm going to ask you a question that was asked a couple years ago at one of the CRA meetings, the Computer Research Associate meetings. It's one of these that gets all the major researchers in computer science, academic researchers together, and talks about what's going on. A bunch of students are chosen to give little short overviews of their research as sort of where things are going. And it was a day of machine learning and regenerative AI, and some department chair from some school got up and said, all this is lovely, but it's not computer science. Computer science is about optimization. It's about getting efficient algorithms. It's about good use of data. This isn't computer science, and I don't know what my department will do. And I heard the frustration's voice. I sought him out afterwards. This is a guy who was trained in sort of a classic 1980s computer science degree and saw the world slipping away and was a little frustrated with it. And I had to break the bad news is that, when you leave a career, it's not that people undo what you did. That's to be expected. It's that they undo it as you're backing the car out of the driveway. But he raised a very interesting point that he knew a certain culture. He knew a certain set of tools. He felt that that was gone and that there was no longer a place for him in the field. The sad message that I had to bring to him was that, in fact, we've never really had control. Computer science has existed in a much bigger ecosystem, that others have asked questions that we have rushed to answer, that we have borrowed from many, many different fields, and that the next generation going forward will have indeed skills that were not his skills. And the key thing in terms of preparing his junior faculty and also his students was the need to be abreast of what's going on, to follow what's not only the research, but how it's being used. And the example that I give is that computer science as an academic discipline was in many ways defined by psychologists. If you look at the literature in the early 60s, J.C.R. Licklider, head of ARPA, he's the one who's defining, these are the problems we're going to solve, these are the ideas we're going to follow, and more importantly for him, this is where I'm giving my money. When Licklider started giving money in ARPA from 1962 to 67, that was the major source of non-commercial research funding in the United States. The National Science Foundation was only giving out money for computer centers, would not sponsor research in any form. Licklider identified AI, machine recognition, graphics, and networking as the key things that he wanted to fund. And those remain central to our field today. And they came from a psychologist. Economists have also had a large role. And I think in terms of looking ahead and looking at your career, what are the economic forces shaping the field? Moore's law had a run, for about 20 years in a very narrow way in the issue of making chips twice as fast and half as expensive. Um, we've been able to carry on some of that after the chips have largely stabilized in about 2006. But it put the industry in the field on a footing of thinking about economic planning, of building ideas, planning ideas for tomorrow's machines. One of the reasons the mobile cloud platform grew so quickly and grew so well is that the people who led it and the people who did the research on it saw it coming as part of the economic force. This is, of course, Herb Simon, who is the one computer scientist to have received the Nobel Prize. But he also kind of grasped and articulated that the managerial decisions about computer, about what would be important, about what we needed to do, would be deeply tied with how the economics of it, how it was being used. So, what are the decisive questions for the future? I love this picture. This is an early Admiral Hopper picture as she's marching off to World War II. The leaders of the field are often done by one generation, by which I mean a group of people with common educational background that come together for a fairly short period, 7 or so years. They often focus on a common set of problems. For example, in the 50s, and Hopper led this, optimal common mathematical routines. The ACM, if you go to its journals in the 50s and early 60s, that's all they're publishing. Common optimal mathematical routines. They move out of it in 64. IEEE floating point, as I said, kills it. But it also forced them, and Hopper made the shift about how optimal ways of communicating with computers, languages, standard languages, portable code. Hopper was there for the first demonstration of a program that could be compiled on 2 different machines of 2 different architectures and run and got the same results. And she helped push us into natural language recognition. Typo there. Natural language recognition that things like Alexa and Siri have become. So where's it going? That's what you want to know. You don't want this lovely historical romp. You want to know where's it going and what does it do to affect you. Is it changing? Yes, and plan your career that way. Will it drop all of the old methods? No, of course not. Things that you've enjoyed, things that have been part of your identity, that'll still be there. Whether you can make a living at it or not is not clear, but it'll still be part of the field. Because will there be some people unable to go forward? Yes, that has happened time and again. That people have gotten to a certain point in their career and all of a sudden they realize that they're going to take radical training to be able to lead a system development or to lead a technical division. Where is the current divide on skills? Well, it's not clear. I think we're in the middle of it for certain parts. And I think in particular, if those 5 fields are not part of your skill set, you're looking at a limited future. Those things being Internet of Things, big data, cloud computing. I have to now remember all the 5 that I had, machine intelligence. Those elements are part of the field now, and they're being used by people outside of the field as black boxes. So if you're shaping how computing is used, those are things that you have to look for. It is a dynamic field, and it is a dynamic field that has advanced human endeavor in very fundamental ways. It serves every kind of human institution you can imagine. Productive institutions, educational, political, the whole gamut of what is done in human right. Early on, a very common theme in the literature was that there was one right way. It was expressed in software engineering as compile once, run many times. That theory, that there was one right way to do things, has not fared well. We have done much better with saying that there are multiple ways. Our goal is to make them work together. The changing questions are inevitable. But the one right now in front of us is, how do we capture human experience? How do we do it at scale? And that's the key thing. As computer scientists, we often live in a very small world. If you look at the number of people who are leaders of our field globally, who help shape the questions, decide what technologies are used, what research is being done, what are the big new systems being developed. Globally, if you do the numbers with generous assumption, 22 to 44 million people max. Most people don't understand these systems the way we do. Most of them can't change the way they're used the way we can. And it's out of 8 billion people, we're a relatively small group. And for that to have an impact on the world at large, there are a number of things we have to do at scale. And we have to do it at scale so that humans have a say in them, so that not everyone's being pushed off the table. That improves the life of all. If we deal with climate change, improves the climate of all, and allows our children to build on them. That's Lois Lurkins again. I am as much as my father's child, I am her child, it's her grandchild, I suppose. As we think about moving our careers forward, we also have to think about moving the careers forward of the next generation of computer scientists and the one beyond that, and leaving for them enough signposts that they can see the way. And that is my talk. Give you a little information about how to get in touch with me, but I'm also willing and able to take questions.
Just as one piece of housekeeping, before we go too far into the question side of it, if you are an IEEE member attending this session, please type in IEEE in the meeting chat.
Yes, we very much want to know who's out there for us, because it's a good organization and it wants to be able to serve you with what you need.
All right, so we will open it up for whatever questions you guys might have.
I have a question.
Yep, go ahead.
So, Dave, do you believe Moore's law is dead?
Moore's law is dead, is the question. Do I believe it? I'm not sure what I believe is important. A couple of things. One, there's an aspect of Moore's law that we were central in building, we being the IEEE, which largely involved certain classes of chips. It ran from 1985 to 2005, roughly. Gordon Moore more or less ran it out of his office, although he eventually got the Semiconductor Association to back him up. They produced quadrennial plans. They marched much of what we remember from that period forward. That's dead. The institution is gone, no one's running it. Do I believe the computers are going to get smaller, faster, and cheaper? That's, again, a belief is not quite the right thing. But there's clear evidence that the end of that arc has not affected the innovation in computers and our ability to get computers in smaller places, to make them faster, to make them cheaper. So one key element of that phenomena is clearly and identifiably gone. We cannot make computers faster just by always making the printing press smaller. But that's not to say the phenomena writ large is gone.
So I had a question I put in the chat, but would the computer human system, is that really the next step in evolution, right? Because computers have capabilities far beyond what humans do in terms of, memory capacity, if you will.
Right.
Yeah.
Memory capacity, the ability to project ahead, the ability to recall and do matching. Yeah, it's huge. This is in many ways Licklider's argument. Licklider was a little less enamored of artificial intelligence back in the 50s than we were. And he argued for computer-human interaction, and in particular, a symbiotic relationship in which computers did the things they did best: information retrieval, calculations, projections, and that humans worked with them and used that to manage things, to make plans, to live their lives, to do all elements. We already see that in so many ways. The question becomes, how is that going to become more formalized? And if you're looking for an aspect of your career that is clearly moving forward, that is indeed one of them. Whether it fits exactly into Darwinian evolution, not that much of a biologist, so not sure I want to speculate. Is it something that is going to help human beings or has the potential of it? Yeah, it does. Should you think about it for a career? Yeah, you probably should.
Yeah, Prakash here. Can I ask a question?
Of course.
Do you see innovation is slowing down? It has peaked now.
I'm sorry, do I hear there's a word that got swallowed?
Innovation slowing down?
Is innovation slowing down? The answer is no, first and foremost. We have as many inventive people working as we do, as we've ever had. They are producing new patents and new products and new services all the time. There's another question, though, is do we see in the field, in the marketplace, in wherever we are, the kind of space for large-scale innovation from a single product or a single idea? That is becoming tougher. And that is certainly, we don't have the kind of wide open field we had in the 70s and 80s when new computer ideas could be tried out cheaply and quickly and be adapted quickly. Yet, there's so much, as you look at what's happened to software engineering, our ability to update large systems on the fly quickly means that there are new innovations being stuck out there. Some we know about, some we don't know, all the time. And that makes just a tremendous opportunity for people. At the same time, is that like deploying Unix in the 1970s? No, it's not quite the same. But we still live in an era when there are problems to solve and there are tools to solve them.
But for lower volumes and markets, is that correct?
Lower volumes, perhaps, finer problems. One of the interesting questions that is out there is when we see the kind of systems we're making with the rapid constant updates, are we in effect producing a dynamic system, and can we project how it moves forward, how it goes, and how it reaches points of innovation? Because in terms of human history, in terms of technical history, we've not been around that long, as computer science hasn't. The cloud mobile computing model, which governed so much of us, is at scale only about 15 years old. And it's likely that after another 15 years, that's going to have to be turned over into something else. There are computer architectures that we think of fondly that all of a sudden dawns on us. It was innovative for only about 10 years, the IBM 360, 370 architecture. You can still get them, you can still run them. It was a big product through the late 80s, but it really stopped innovating after a decade. We're longer than that into cloud computing. What's going to happen there? The Intel model architecture for chips, that had about a 20-year run as a point of innovation. There are going to be new points, and I think Christensen's key insight is pressure will build and the innovation will come in sudden turnovers. But that turnovers may be built out of a lot of small pieces.
I have a question.
Sure.
When you look at physical neuromorphics, in other words, neuromorphic architectures and actually physical constructs,
Yep.
Where do you see that on the landscape and where that ends up in terms of computing?
That's a good one, and I'm not sure I have a really good answer for it. In terms of my last answer, it's one of those things that could build up with other tools that all of a sudden we realize this is central to our lives, and we have no idea. I'm not as current on it as I am on other things. My feeling is that it's marching forth, that people are working with it, there are opportunities there. But I'm really hard pressed to say, where is it going to be? It would not surprise me if it was like a lot of technologies that has a bit of a flash, people get some ideas from it, and it gets merged into something else. At the same time, it could also be an interesting brick in the wall, if you will, that leads to a major turnover.
I believe Jenna Hall had asked a question in chat, and then I believe
Okay.
it would be the last question for tonight.
Okay.
You have to scroll up.
So it's my turn, or it's a Jane or somebody else's turn?
So we're going to answer Jenna's question first, and then we'll.
So I need to look at
next
chat,
question.
actually.
Yeah.
Okay. Where has chat gone?
Oh.
Here it is. Jenna. As a student coming into a field, I feel a little overwhelmed with the expansion of innovation happening right now. Do you have any advice for finding focus or discovering a path in the computer science field? Dear Jenna, I have advice. Whether it's any good or not is for you to judge. Computing is best learned. This has been true throughout its history and is certainly true now. When you connect it to something that interests you and something you love and something you want to explore. And it's that key bit of wanting, of desiring to explore that I think is important. I'm of that generation that came of age with BASIC and games. I had had a good experience in my father's company using his computers and getting a lot of computer science, but what took off is programming our own games. That led to other things and pushed me down a path into certain ideas that became the basis of my career. In looking at what you have got now, there are things that interest you about what you can do with computers. And being able to ask the question, how can I make this bigger? How can I generalize it? What is the key element that I can use in it to solve my problem and solve other problems is just very helpful. In the aughts, one of the things that comes out with mobile computing is the recognition that it can be used to build markets. And we have done a lot of market building that did not exist in the 2004, 5, 6 timeframe that we now have. It was not completely anticipated, but the idea that you could go to eBay, to Etsy, so all these things that were markets provided by small providers simply didn't exist. And people experimented with them. Some failed, some didn't. Some got merged in with others, and that led to it. As to what we have, as you think about what you're doing, what interests you in the technology, and what interests you in the people around you, the institutions, the activities, and ask yourself, how can I put those together? That would be my advice. All I can do is give the caveat that comes with all advice. It worked for me, or at least I remember that it worked for me. And I hope something like that will work for you. And then, Lai, you have a question?
Yeah, I do have a question. I hope it can be a good one. And the thing is, during in between, I had to pick up a call, so I missed probably 20 plus minutes of your presentation. I hope I didn't miss the most important one. But my question is about LLM and Chat GPT. Essentially, what I see is because of the development, now computers, AIs can chat like an intelligent person, or you can even argue it may seem more intelligence than average Joe, than your neighbor, than even average. You can even say average college graduate or average high school graduate. So that's probably a perfect computer history question. So from your perspective, from what you know, is it more a commercial thing, like it can, have going to have a huge commercial impact, or is that really the paradigm shift? I mean, some leading practitioner predict Armageddon. I mean, and they call 1 year ban for this sort of research, right? Is that called for, or is that totally overblown from your perspective? I really want to hear this. Yeah.
I'm glad to offer what is, after all, my perspective, and it's a perspective from a historical and also a bit of a perspective from a sociological point of view. Right now, which is to say today's the 17th, right? August 17th, 2023, we're in the middle of being kind of slapped in the face by generative AI. And we're a little bit shocked at what's going on. We're surprised in a way we were not surprised 10 years ago with self-driving vehicles. We had a little bit of a ramp up in self-driving vehicles. We'd seen some of the demos, we'd seen some of the car crashes. And as they got better and better, we were able to merge with them quicker. Chat GPT hit us very suddenly and hit people who had not thought much about AI and who had not followed it over the years in a very quick way that shocked and frightened them. If you start probing some of those responses, some of the things that these programs come out, they're impressive, they're good. The question that you need to ask for yourself, is this a program that you would use as a colleague in business? Would you always rely on it? How would you do to question its judgment? What would you do to make sure that it was giving you good ideas? Would you always trust it? Would you change the way you behaved based on what it did? Would you change your behavior to change its behavior? All of those questions haven't been really sorted out yet. And that's what the next couple of years are going to be. It's going to, I think at the end of the day, we're going to be surprised, and you can already see it. You see things that are cute, that are clever, but it doesn't have the kind of reliability that would make it a product, make it a colleague, make it something that you would modify your life to work around it. At the same time, it's powerful technology, and it will be incorporated in things, particularly large scale things, that we have difficulty handling now. My claim is, first and foremost, it's going to become the default statistical analyzer, that it will model human behavior, it will model what's going on data and tell us what's going on. We as computer scientists need to figure out how you validate that, how you check it, how you tell it it's wrong, and how you go against it, and what reasons make sense. In the process of taking that role, it's going to push out of jobs a number of workers who have worked with information, who work with numbers, who work with data, and their position will vanish. It will probably take a certain amount, or back up a certain kind of person that is, working with human beings and needs a large backup. Those jobs have already been impacted by technology, and this is just another step in it. However, it is also, at the end of the day, one more step in putting a clear dividing line. And if you look at all the graphs, and I can't do it here, but it's that the world is becoming kind of double humped. There's a big low skill hump with people who have basic skills, who work with technology and work with jobs, but that the technology becomes a barrier for what they can do. And there's this much smaller lump of people who govern it and control it, and there's not much in between. The story that I like to give is what's happened to restaurants since the invention of the computer systems that manage orders. Once upon a time in restaurants, it was a great way to get a start as a job as a 20-something or as a teenager. You didn't need any skill. You came in and you could work your way up. You'd be given the bad tables and the ones that didn't tip well, but you could move up first to a cheap restaurant and gain skill and become in a more expensive restaurant, and then you could become manager of restaurants and all of that. But it was something you could do, and the distinction between waiters was substantial. In this day and age, as we now have a computer system that sends orders to the kitchen, it prioritizes them, it schedules them, it identifies where they're to be delivered. And so that we now have three kinds of waiters. We have waiters who basically are there for human services. They work with the table, they take the orders, they make sure that the table gets what they want. If someone says my food is bad or I don't like it, they're the ones that have the authority to fix it. Below them, there are food runners, and these are people who take plates from the kitchen to the table. They don't know what they're doing, they just know they have 2 plates. This goes at place 14, this goes at place 13. That's what they know. They don't have control over the system, they don't interact with the customers in the same way. There's a technological barrier between them and advancing. And then at the other end, there's the person who knows the system, who can change the system, who manages the system, who sets it up for desired outcome. And there's one of those. And we're seeing that kind of stretching. And you can even stretch it one notch farther. This has also created busboys, although we've always had busboys, people who often don't speak the right language, who can only clean up and there's nothing else. But it stretches out the division of labor. And that's clearly going to happen to greater extent. What kind of society is that going to produce? I have some ideas. Are we going to have to deal with the tensions created by that society? We almost certainly are. Are we prepared to do so? I think we're going to need more experience before we really are. But that's the challenge we face as a society.
Okay, very, very insightful. Thank you so much.
Thank you. If that's my last question, I'm always willing to take questions. First, feel free to contact me. I have long experience with the IEEE and certainly want to help people use the IEEE and particularly the Computer Society well. I'm always glad to hear about new ideas and always glad to take new questions. You have
Thanks.
my email address, and I look forward to hearing from
All right, so I think that's going to do it for tonight. There is one more session left. So one final session, the Careers in Tech Summer Series. That will be on August 31st. So for those of you that have been faithfully attending every session, you have a 1-week break. And then we'll be back again on August 31st. There are already plans being worked on for a fall series. It will probably not be every week because, as you can imagine, there's a lot of effort that goes into putting the stuff on every week. But in the meantime, thank you for your attendance tonight. The session for the video for tonight, as well as the one for last week, will hopefully be up over the weekend. So I can catch back up because I know I'm one session behind right now. And other than that, thank you to our speaker, and thank you everyone for attending tonight. Have a good one.
you.
Thank you. Bye-bye.